Welcome to this in-depth session about polygon mesh processing in the computational geometry algorithm library. My name is Sebastian Oriot, and in this second part, I'm going to give you a light and graphical overview of the algorithm for polygon mesh processing that are available in CGAL. Let's start by low-level tools that are used across the various packages. The axis-aligned bounding boxes tree is a data structure that constructs a nested hierarchy of axis-aligned boxes with the leaf nodes containing a set of input primitive. This is a generic data structure in the sense that the user provides the definition of what a primitive is. In the case of triangle meshes, there are two predefined types, which are the segment edges or the triangle faces that can be used as primitive. This means that the tree will be built either based on the edges or on the faces. Then, using this tree, you have a set of functions that allows you to get a pretty fast answer to the question you are asking. So if we take, for example, the doIntersect function, you can provide him a query type like array, and you will know whether the ray intersect the object stored in the tree. It is really important to choose the right type of primitive, because if I'm choosing the segments corresponding to the edges of my mesh, then it is unlikely that I will get an intersection with those segments. But if I'm using the triangles as primitive, then I will probably have what I'm expecting to have. So this tree can be used to, as I said, know whether you intersect the mesh, but you can also get all the set of primitives that are intersecting by your mesh with any type of primitive. So let's say I can take plane and I will get all the faces that are intersected by my plane. And I can also do some kind of retracing by getting the first primitive that is intersected by array. But I can also do closest point location with this structure, which was used to produce this picture. So for any point in the plane, you check the closest point in the mesh, and then you can assign it a distance, and then you get this pretty nice picture. The second structure I want to introduce is actually an algorithm, which is box intersection detection. This algorithm takes as input a set of boxes and a function that will be called each time two boxes intersect. The basic way to do that is you have two loops, and then you are trying to match all the boxes to check whether they intersect, and you call the function over it. But this function is constructing a hierarchy of bounding boxes on the fly, so the tree is not sorted, but you construct each level of the tree one at a time, and then you discard the previous level. And this allows you to filter several boxes at the same time and makes that faster. An interesting thing about this algorithm is that it is working in any dimension, so 2D, 3D, and T dimension. Another type of function that are provided are the Euler Operation for doing some basic operation on meshes, like splitting an edge, splitting a face, collapsing an edge, etc. And there are also some wrappers, like the face filter graph, that allows to see any mesh data structure as a restricted version. Let's say you have the basic usage of this is you have a mesh with several connected components, and then you want an algorithm to only see one part of your mesh. So you define a face filter graph over the connected components. Then you have the dual adapter that take the dual view of your mesh. So let's say you want to get the shortest path, well, not necessarily the shortest one, but a path between two faces on a mesh. Then you take the dual of the mesh and you can call a Dijkstra's shortest path algorithm over it, and then you will get a path connecting your two faces. And the sim mesh, it's an abstraction that of a mesh that allows the user to define a virtual boundary, a sim, over a mesh. So a closed mesh can be seen as open with a virtual boundary, basically. I will come back to this later in the package that is using it. There are also a set of functions that enables you to do some selection of simplices over a mesh. So you can select vertex, edge, or face, and you can expand or reduce this selection using the neighborhood of those simplices. You can also collect simplices incident to another one. There is a wrapper to the Metis library. So the Metis library is a library that computes a decomposition of a graph in different components. So here we have written a wrapper around this library, and then, so given a mesh, you can compute a decomposition of this mesh. So this is useful, for example, if you want to write some parallel algorithm over a mesh. You first compute a decomposition of that mesh, and then you do what you want to do with each component of the mesh. And there is also some point location facilities. So given a point that is on a mesh, you want to know to which face it belongs and to get the barycentric coordinates of the point inside that face. Okay, now I'm moving to the higher level tools that are available in the CGAL library. Okay. So here, the intersection test. So you have two triangle mesh or a triangle mesh and some polylines, and you want to know whether the mesh intersect. So this can be done using the box intersection D package I was mentioning earlier. And it can also give you, if you have a set of meshes and not just two, all the pairs of meshes that are intersecting. The self-intersection detection. So given a mesh, you want to know whether you have some triangles in the mesh that are intersecting along a simplex, well, that are intersecting not along a common simplex. So adjacent triangles do not intersect because they are sharing an edge, but as you can see on the picture here, this triangle is crossing several that are geometrically close to them. Then you can compute for a set of points whether it is inside, outside, or on the mesh. So here, this struct side of triangle mesh, you construct it once with your input mesh. Internally, it builds an ABB tree, and then you can do many queries. So you can do some queries of points over your mesh. Similarly, you have the polygon mesh slicer. Same thing, you construct the class with the input mesh, and you give a plane, and it gives you the polyline intersection, if they exist, of your mesh with the plane. There are also some distance computation between two meshes. So here, the approximate Hausdorff distance and approximate symmetric Hausdorff distance are taking as input two triangle mesh, and for those two meshes, you want to know what is the distance between those meshes. The implementation is basically similar to the Metro paper, and it's based on the sampling of one triangle mesh and compute distance to the other. And in the case of the symmetric, it's done twice with a sampling on the other mesh. You can choose what kind of sampling you want to have, and the number of sample points you want to take, and etc. So the more points you have, the better will be the approximation. 3D Boolean operation using corefinement. So this version is a restricted version of Boolean operation. The input needs to be some closed triangle mesh, and triangles intersecting are refined, meaning that the intersection between two triangles between mesh A and mesh B are inserted inside a mesh, and then the meshes are cut along those intersection edges, and patches are glued together so that the result is the output that you are expecting. So here, an interesting feature of this algorithm is that you can compute several kind of operation at the same time, meaning that you can compute the union and the intersection at the same time, but also the fourth type of Boolean operation. And you can also do in-place operation, meaning that you are going to update a mesh instead of creating a new one containing your operation. So let's say I have a mesh and I want to subtract a given part. Then I'm not going to, I have the possibility to not copy the whole mesh, but just update the mesh with the removed simplices from that mesh. So one limitation to this is that the output must be manifold, and otherwise then nothing will be computed. So if you want to do some operation with some non-manifoldness, there is the slower package Nef Polyhedra that can represent stuff like that. So you can have an edge attached to the middle of a face, or you can have some non-manifold edge here. So these two cubes are sharing an edge. So the implementation is slower because the way things are represented is that for each vertex there you have a small sphere, and you are storing an arrangement on the sphere of all the faces and edges incident to that to the vertex. If you have a hole in the mesh, you can use the hole filling package to fill it. The simplest method, triangulate hole, will fill it with triangles using only the vertices of the hole. If you want to add extra vertices to match a given density, you can call triangulate and refine hole. And if you want to also try to preserve the local curvature, you can use triangulate, refine, and fair holes. Two versions of these methods are available. One that use the complete n-cube search space of possible triangles, and another version that use the search space of triangles that are in the Delaunay triangulation of the points of the hole. The isotropic remeshing function, it's an iterative process that takes a triangle mesh and a set of faces that you would like to remesh isotropically, and you are iteratively doing some edge split operation, edge collapse, flipping some edges, and moving the vertices to smooth the mesh. And you can optionally reproject the input vertices on the original mesh. So here we can see an input mesh. In red, you can see sharp edges that you would like to preserve after the remeshing. So that's what you see on the top picture. So here you have a mesh, and then you just say, okay, I give you a target edge length, remesh it, but please preserve my edges. So preserve here in the sense that they are the feature are geometrically present, but the edge are obviously split. You have the option of not splitting the edge if you want. So as I was saying, you can pass only a subset of faces of the mesh, like in this case, and only this part will be remeshed. And as you can see here, this part is connected to the other one with all those triangle fans. Okay. The Surface Mesh Simplification package is a generic framework where you give an input triangle mesh, and edges are first sorted using a cost function that will tell the algorithm how much does it cost to collapse an edge. So we will first handle edges that have the lower cost. Then each edge is collapsed, and the position of the points replacing the two that have been merged is computed using a placement. And we stop trying to collapse when the stop function say that we need to stop. Additionally, the user can mark some edges as non-collapsible, which is sometimes really important. For example, if you have some interfaces that you want to preserve. And this framework is generic in the sense that there are different cost, placement, and stop function available, and the user can provide their own implementation. The Subdivision package provides you access to the classical subdivision mask, so like Carlton Clark or Loop, Sabine, etc. And it works on both on closed and open meshes. The Variational Shape Approximation package. This package takes as input a triangle mesh, and it's a framework that tries to fit some proxies to minimize a given error metric. So the proxy is defined by the user. So in this case, the proxy is a plane. So we are trying to fit a plane proxy. You can also define several metrics for the error. So the error here provided by CGAL is the L2 and the L21 metric. And as soon as you have fitted those primitive over your mesh, you can compute another mesh with which approximate the input mesh with the primitives. So here we have a new mesh with each face being one primitive, which is planar. We have an algorithm for smoothing mesh elements. So here we have some triangles that are not well shaped. So the smoothing method will iteratively improve the quality of the triangles, as you can see on the picture. There is also shape smoothing. So this one is somehow different because now that's the global shape that you want to smooth and not the element. So as you can see, the more you apply the function, the less details the mesh has, and it will eventually converge to a sphere. Convex Hull package, classical thing, but the interesting thing is that you take a triangle mesh as input and you get a triangle mesh as output, so that you can apply other algorithms directly on the Convex Hull and it will just be a triangle mesh. The Deformation package, based on the as rigid as possible deformation framework. Here you have a triangle mesh and no skeleton at all. You are just defining a set of points, region of interest, that are allowed to move, and a set of control points to which you apply some constraint position. And then the rest of the mesh will deform to try to minimize the deformation energy. The Segmentation package. This one is based on the notion of local thickness for a given face of a face to a mesh. The default version being based on the shape diameter function. It consists of taking the centroid of any triangle face and to shoot several rays in the inside of the mesh, and then you are doing the mean of the distance of the intersection segment that is inside the mesh, and then this gives you locally the shape, the diameter of the shape at this point. And using this estimation, you can compute a segmentation of the mesh, which is regularized using a graph cut algorithm. As I was saying, you can define your own thickness. Like, let's say you have a skeleton and you define the distance of the skeleton to the mesh. It will be working also. The skeletonization package used the mean curvature flow to iteratively contract the mesh in the inside. And when the contraction step has converged, then you extract a 1D skeleton out of the contracted mesh. Interesting thing to notice here is that you can control the speed at which the mesh is contracted, and the more time you spend, the less deformation you apply at each step, the more accurate will be the skeleton. Accurate in the sense that it will be well centered. And as I was saying, you can use that because as soon as you have the skeleton computed, then you get a correspondence for each point on the surface to the skeleton, and you can use that, for example, for doing a segmentation if you want. The parameterization package. So this package takes a triangle mesh and you want to apply overrated texture. So like here, I have a triangle mesh of a hand that I want to wrap in 2D. So that's what you see here. And I'm putting a 2D grid, a regular 2D grid over it, and then I'm putting back the grid in 3D, and here is what you have. The algorithm, depending on the algorithm, some of them needs to have a boundary. So here, for example, this is mapping an open mesh to a disk, and then put the parameter, compute the coordinates of the 2D coordinates of the vertices on the circle. So you need to define here, as you can see here, a virtual boundary in my mesh. So this is where the sim mesh I was mentioning before comes into play. I'm defining those red edges are defined as a virtual boundary, and then this makes the algorithm think that it's something open that it can map into a disk, a 2D disk. But it's not the case for all the parameterization method available in CGAL. Here are some methods available in CGAL, and you can see that they have different properties. So some are preserving the area of the elements. The other are preserving the orientation of the element and the angles of the element. Geodesic shortest path. So this algorithm takes as input a set of sources, and then it computes a data structure onto which you can do queries to get the closest point to your query. The closest point among the sources that you have selected, as well as the path, the geodesic path, meaning not only a path that is not only going through edges, but only that can cross faces. So shortest path from the point to one of the source vertex that you've been selected. There is a package that is using the heat method for computing approximate geodesic distance. So here, similarly, you define a set of sources, and then in a one pass, the algorithm computes for each vertex in the mesh the distance to the sources that you have selected. So in this case here, I've put one source under the feet under the feet of the elephant. So there are 4 sources, and here is the isoline distances you have to those 4 points. So one thing I haven't said for all the algorithms that I mentioned before is that it assumes that the meshes are clean, in the sense that they are manifold meshes and that they do not contain self-intersection. So a mesh is manifold basically if you take a small sphere at any point on the mesh, the intersection with a small sphere will always be a disk, basically. So here you can see that this mesh is not manifold, because if I'm taking a sphere on the edge, then I will not have a disk, because there are 3 triangles incident to that edge. The other type of issues that you can have, I said, are self-intersections. So in this case here, you can say, okay, there is a problem of conforming, but no, there is a small triangle which is degenerated. So the three points of the triangles are aligned, and this define a degenerate element in the mesh and the self-intersection. But you can also have real self-intersection. So in this model, I have a cube with one vertex on the bottom face, and I'm putting the vertex in the top direction so that it's crossing the top faces. So this is one type of self-intersection, and the second type of self-intersection is here. Then you have this point that has crossed that edge and make the triangles overlap, while, well, it should not have been like that. So these are the type of defects that the algorithm doesn't like and needs to be fixed before calling the functions. So CGAL provides a few tools to to fix those issues. So the first thing is when you have a file containing some triangles, it might not represent a valid triangle mesh first. So here on the left picture, I'm representing a cube that is meshed, and the color associated with the triangle corresponds to the orientation of the normal. So the light color means that the normal of the triangle points outside, and the dark color means that the normal is pointing inside. So let's say you have a mesh with an indexed type for your vertices, and the triangles are like that. So this is not triangle mesh. There's a function in CGAL that enables you to orient this, meaning that it will take one triangle and by diffusion will try to exchange the order of the vertices of a triangle so that the triangles are compatible. If it's not possible, then it will detect that the edge is non-manifold, and is going to duplicate that edge so that you can at least load that into a triangle mesh. But obviously you will get a self-intersection because you will get an edge intersecting another one. If you have some degenerate elements inside, you have some function to remove those degenerate triangles directly before creating the mesh. And on the right side, you can see the result after the orientation of the triangle for this soup. So as soon as I have my triangle soup that is oriented, then I get a triangle mesh, always. It's always giving you a triangle mesh, but potentially we'll have some self-intersections created by the non-manifold edges or non-manifold vertices. One kind of defect that can be repaired is when you have a boundary that is between the triangles. So on the left side you can see, for example, this edge here, this one here. So it's in red because it's a boundary. It means that the edge is not the same. The edge between the triangle which is above and below is not the same geometric entity. You can fix that by calling the stitch border function. So now on the middle picture you can see that I no longer have those edges as boundary. I only have this small gap, And then what you can do to close that gap, instead of calling the all-filling function, because if points are really close together, you don't want to introduce really small elements. So what you can do is you can call the snap function. So it's a non-documented function because it's not yet, we are not yet happy with the behavior in all the cases, but at least it's working pretty well on most of the cases. So the interesting part is that, like for this point, you can see that it does not have another vertex in the other face. So what will happen is that the triangle will be refined so that there will be a point to be snapped together. And then after having called the snap function, then the mesh is closed at this part. There are also some undocumented functions to repair degenerate elements, so to remove degenerate elements. We have also some a function that is documented, this one, that remove almost degenerate elements that are called caps and needles. You can also remesh self-intersecting patches. So let's take this example here. So here you have the same case I was describing before, where you have a point that crossed an edge while it should have been on the other side. And the function is taking all the faces that are self-intersecting and remesh that patch. And then you can see that here we remove those self-intersection. For the case of the bottom vertex that was crossing another face, which is not, I would say, a local issue, because it's not just like you have when you have a rounding issue, for example, you have the problem I was describing on the left, but here it's more like a really geometric issue that needs to be fixed separately. So also here there is a function that is called auto-refine that inserts the intersecting edges between the triangles inside the same mesh, and then you can filter out some parts if you want to have a valid manifold triangle mesh. Now I'm going to describe two new packages that have been recently added to the CGAL library, actually to the 5.1 release that is not yet out, but that should be out during the summer, I think. So the optimal bounding box package, it contains a first implementation of one algorithm to compute a non-axis aligned bounding box that tries to minimize the volume enclosed by the bounding box. So here the function returns a transformation matrix so that the axis, you apply the transformation to your input mesh and then take the bounding box, and that bounding box is one that is close to the optimal for the volume. And then you can also apply the inverse transformation to get the box, and obviously there is one function that is giving you that box directly. The second package that has been added to the release is the surface mesh topology package. So for now, what does it contain? So you have a triangle mesh, and not necessarily triangle, if I remember correctly, and you want to compute the shortest non-contractible cycles, meaning that it's the shortest sequence of edges in the mesh that cannot be contracted. So if I'm taking, for example, a cycle here on the here of the elephant, you can see that I can always collapse it to a point. So it's not, there is no non-contractible cycle in here, but here on this part, and as well as on the tail, there is a non-contractible path. There are also some functions that enables you to test whether a curve is contractible and whether two curves are homotopic. This concludes this presentation about algorithms operating on polygon meshes. All the algorithms presented here are using a similar API and are operating independently of the meshing type. I invite you to visit the documentation website to get more details and to see more examples.